Welcome to This Explainer. Today, we are absolutely not just staring at letters on a page. We're actually uncovering the invisible language that runs the physical world all around us. You know, for a lot of people, algebra feels like hitting a brick wall, mostly because it suddenly throws all these random letters into a subject that was supposed to just be about numbers. But today, we're reframing that completely. We're going to discover how these abstract concepts actually form the predictive code of the universe. Okay, let's take a quick look at our roadmap for today. We'll start with the language of algebra, then move on to the order of operations, working with variables, evaluating algebraic expressions, and finally, we'll see how algebra plays out in real life.
All right, part one, the language of algebra, or as I like to call it, the ABCs of math.
So think about it like this. You really can't read a book without knowing the alphabet, right? Well, you can't do algebra without grasping its core vocabulary. And the star of the show here is the variable. A variable is simply a symbol, usually a letter, that represents an unknown or changing quantity. Instead of just dealing with static numbers, a variable lets us point to a general principle. It might stand for some mystery number we're trying to track down, or could represent a whole range of possible numbers. It's basically the ultimate mathematical wildcard. Now, when we take these mathematical wildcards and combine them with regular numbers using basic arithmetic, we build what's called an expression. Imagine numbers just hanging out on their own. Pretty boring, right? But when you link them up with variables using addition, multiplication, division, or even exponents, you create a dynamic mathematical phrase. And here's the absolutely crucial differentiator to remember. An expression does not have an equal sign. It's just a combination of values and operations waiting to be unpacked. Let's take a look at the actual anatomy of an expression. When you zoom in, you'll see it's broken down into some very specific pieces. First off, notice the terms. Those are the chunks separated by addition or subtraction signs. Inside those terms, you're going to find coefficients. Those are the numerical factors sitting directly in front of the variables, basically multiplying them. And finally, you've got your constants. These are the single numbers just hanging out all by themselves without any variables attached. And their value is, well, constant. No surprises there. Moving right along to part two, the order of operations, essentially the grammar of math. So if expressions are the phrases of our new math language, the order of operations is the strict set of grammatical rules telling us exactly how to read them. Think of this as an unbending hierarchy. You have to evaluate things step by step. You handle parentheses first, then your exponents. After that, you break any ties between multiplication and division, or addition and subtraction, by simply reading left to right. This isn't just a polite suggestion, guys. It is the absolute bedrock of algebra. Need proof? Just look at the expression 3 times 2 plus 7. If you just read it blindly and add the 2 of the 7 first to get 9 and then multiply by 3, you end up with 27. But the grammar rules state multiplication has to happen before addition. So 3 times 2 is 6. 6 plus 7 is 13. Getting a wildly different answer just by changing the order really proves why these rules are non-negotiable if we want to avoid pure mathematical chaos. Now, when you're confronted with something that looks absolutely horrible, like a massive fraction-filled expression, it is so easy to feel completely overwhelmed. I totally get it. But here's the secret trick. Treat the numerator, the top, and the denominator, the bottom, as if they have invisible parentheses around them. You evaluate the entire top, completely separate from the entire bottom. Simplify both of them down to single numbers, and only then do you let them interact through division. Work it down logically, and that terrifying complexity simply vanishes. All right, part 3, working with variables, reading the math sentence. We're now transitioning from purely numerical work straight into the heart of algebra. Math educator Kirk Wheeler points out something super important here. You shouldn't have to plug a number in just to grasp what an expression is trying to tell you. You really need to be able to scan it with your eyes and immediately understand the exact chronological sequence of events happening to that variable. For instance, reading 3x minus 8 properly means recognizing the actual narrative of the expression. The story goes like this. You take a mystery value, you triple it, and then you reduce it by 8. If you actually went ahead and replaced x with a number, you'd do the multiplication first because of that coefficient sitting right next to the variable. What you are most certainly not doing is taking x, subtracting 8, and then multiplying that whole result by 3. The order totally matters. That brings us to part 4, evaluating algebraic expressions, or putting numbers into action. So let's say we have the expression 4x minus 7. Now, this expression actually has infinite different possible values depending on what x happens to be on any given day. But right now, we're going to declare that x is exactly 5. So take a quick moment and mentally evaluate this. What actually happens if you substitute the number 5 right in there for the variable x? Notice the best cactus we're using here. Whenever you substitute a number for a variable, always put it in parentheses. It's a great visual reminder that the 4 and the 5 are multiplying, and they aren't just suddenly mashing together to become the number 45. So, by carefully substituting our 5 in parentheses, multiplying them to get 20, and then dropping the 7, we land right at a final result of 13. Easy, right?
And finally, part 5, algebra in real life, solving the real world.
To truly master all of this, we really have to look beyond the textbook. Because very often, variables aren't just abstract letters floating in space. They stand for real, tangible things. Think about a business owner. They don't know in advance exactly how many people are going to show up for a tour on a random Tuesday, so they create an algebraic model. In this example, the expression 12 times the quantity n minus 4 represents their total earnings. Suddenly, the math is acting as a powerful predictive tool for a real-world scenario. So, knowing our expression and our trusty order of operations, can we figure out the company's revenue if exactly 14 people show up? Now we're taking that predictive model and testing it against concrete reality. We are simply replacing our variable n with a known quantity. Let's do the math. Parentheses go first, remember? So 14 minus 4 gives us 10. Multiply that 10 by 12, and just like that, boom, you've got $120. We literally just used an algebraic expression to predict a real-world business outcome. The math just works seamlessly. Think about it. Whether you're adjusting a family recipe in the kitchen to feed a larger crowd, or maybe you're setting realistic fitness goals based on your daily workout metrics, algebra really is the invisible language of the real world. It's the ultimate tool we use to manage the unknown. You've now got the vocabulary, the grammar, and the structure you need to decode these everyday mathematical sentences. So the only question left is, what unknown quantity are you going to evaluate next?